Hi. It's Saturday again. Every 7 days. And we are supposed to look at some problems that you might be interested in. So what are those problems? We have problems. Let's see.
That's 2 please from a homework.
Great, 2 problems from homework. This one is section 4.7. It says use the limit methods to determine which of the 2 functions grow faster and state if they have comparable growth rates. Yes. So let's see. So use the limit. So this is problem 21 on homework. And we are supposed to compare ln x to 14 to ln x. Well, we are going to take the limit as x goes to infinity of ln x to 14 divided by ln x. We can use the formula that will take the 14 in front of the limit, in front of the ln. And the limit is 14. Now, we don't really have to use L'Hopital rule on this one. You can. We don't have to. Since the limit is finite value, they grow at comparable rates. Both functions are of the same character, right? The one is 14 times larger than the other. But that's it. They are the same type of a function. And they are both raised to the same power. This x to 14th sounds like it's a big deal. And it is a big deal if you are comparing x, which is linear, to x to the 14, which is not linear. But within log, you see that 14 jumps in front and is just 14 times larger. So the limit is 14, and they grow at comparable rates. When we did the comparison of function, I believe we did that on 4 point. Let me just see, all the way at the end. Yeah, there it is. So they both fall under ln to the first power x. They both fall under that category. So they are not even in different categories. It's not this one because it was 14 times ln x, not 14x or x times ln x. It was just 14 times ln x. That's a constant, not x to the p. So both of them are in this right here. So that's the first problem. The second one, actually it's supposed to be, the first one was 19, same homework. It says limit x goes to infinity. Did I? Whew. Okay, good. For a moment I thought there was no stream. 1 plus 9 over x to the 6 raised to the x to the 6. So the way to do this limit would be to use the ln again. Y equals limit x goes to infinity 1 plus 9 over x to the 6 to the x to the 6. And then we put ln in front the both sides. We have ln y is equal to the limit x goes to infinity. And now we drop x to the 6 in front of ln. And then we have this. Now what we do is we check, and we get infinity times 0. Once I have infinity times 0, we can use our 1 over f trick. Nice. So ln of 1 plus 9 over x to the 6 divided by 1 over x to the 6, which gives me 0 over 0. So now we can use L'Hopital rule to take the limit. We take derivatives of numerator and denominator independently. So the denominator is going to be negative 6 over x to the 7th power. And the numerator is going to have 1 plus 9 over x to the 6, sorry, there. And its derivative on top, which is 9 times negative 6 over x to the 7. What happened? Okay. X to the 7. Because when we are taking derivatives of ln, it's f prime over f itself. So f is the entire parenthesis, and then its derivative. So we have 9 times the same thing like here. So now they will cancel completely. And I just want to see we can, nah, that's good enough. So what we have is 9 over 1 plus 9 over x to the 6. That's what's left. When this goes to infinity 0, the whole thing is 9. We have that ln y is equal to 9. We e both sides. And then y is equal to e to the 9. Which is what we were looking for, because remember in this step I set y to be equal to the entire limit, and now we have down there that y is equal to e to the 9. So the limit we were looking for, which is x to infinity 1 plus 9 over x to the 6 to the x to the 6, is equal to e to the 9. That's the answer. Now I would like to show something else. When you get, if you get more into calculus and these calculations, you will find out something interesting. Once you see the mathematical form, you might know how to approach it differently. So as soon as I saw this problem, I knew that the answer was e to the 9 immediately, without thinking, because I know mathematical form for special number e. What I know is that the limit, let's n goes to infinity, of 1 plus 1 over n to the n is e. And then I also know the expanded version of that, which is limit n goes to infinity of 1 plus r over n to the n is equal to e to the r. So as long as these two are the same, this goes to infinity, whatever exponent is here, it's going to be exponent of e. Now you say, but I have this x to the 6th. And I say, so make a substitution. N equals x to the 6th. So from where x is equal to 6th root of n, if you want to, limit 6th root of n goes to infinity of 1 plus 9 over n to the n. Good morning. So now, as you see this, you say, well, what the hell is going here? Well, don't worry about it, because when you put the 6th power to both sides, you get n goes to infinity to the 6th, which is still infinity. It is clearly e to the 9, if you know the formulas from before. So once you know the definition for e, this is the definition for e, and this is the expanded version because of the r that can appear there. No matter how this problem looks like and what it has here and the number there, you can immediately answer these questions. And as you do this, now obviously this is something that you get through experience in doing many of these problems. There are also versions, if you say 1 plus, this is a sneaky one, 1 plus 9n to 1 over n, and then n goes to 0. When you do the substitution, you actually get back. I'm going to write it. It's not. Well, you know what? Since I wrote this here, I solved this problem by substitution. Now I'm going to modify it. So limit x goes to 0 of 1 plus x to the 1 over x. This is e. Now, how? Why? Substitution is n equals 1 over x, from where x is 1 over n, if you solve it. So now, you have that the limit x is 1 over n goes to 0 of 1 plus x is 1 over n, and then 1 over x is n. And you can clearly see that in the limit, if n is going, in order for all of this to go to 0, n has to go to infinity, because 1 over infinity is 0, right? So you can replace this with n goes to infinity, and you get the exactly definition for the limit. So they can be, they can be hidden. These substitutions are very, very useful to know as you solve these things by hand. And we are going to use these substitutions in 5.5, integration by substitution, and it's going to be one of the most important techniques for your calculus 2 survival, for all of you going to Calc 2. Anyone? Oh, that's almost everyone. Okay, I see. You're not going to Calc 2? Calc 3 after that. I'm going to do Calc 3, you're going to do Calc 2. No Calc 2? No, I'm definitely going to calculate. I don't do it so hard this semester. I do it every semester. That's how bad I am at calculating. Do what? Okay. All right. So these are your two problems. Yes. I can't give you anything. All right. Anyone wants to buy used iPhone? 35 bucks, that's it. iPhone. It's too much now, right? They kill it. Yeah, I killed it. All right, fine. The next problem is another one from 4.7. Clearly, we are taking the limit. And I will start this problem by making a graph for ln x. Just to note that as x goes to infinity, y goes to infinity as well, because the graph is constantly increasing to the right. So we know that ln of infinity is infinity, in which case we know that this is infinity over infinity. Make sure you are not using the formula for this, because there is no formula for this. The formula is for ln x over y, not for ln x over ln y. So there is no formula for this. We actually have to do the work. So since we have infinity over infinity, we are going to take derivatives. So we are applying L'Hopital's rule. We still have the limit. Don't forget the limit, guys. It's 5 points per step per problem. So the limits are taken by copying the function as is, the argument, in the denominator and placing its derivative in the numerator. And as we take the derivative in the denominator, it's going to be 3x plus 4 and then 3 on top. We still have the limit. X goes to infinity. And now I have 2 times 3x plus 4 times 3 times 2x plus 5. And I hope you see that the limit is 6 over 6, which is 1 from there. If you distribute 2 times 3x is 6x, and then on the bottom 3 times 2x is 6x. So they obey the polynomial rule, right? The same exponents, just take front coefficients. Front coefficients are 6 over 6, which is 1. So the limit of this expression is 1. Derivative of 1 is 0. So plus 0, right? So derivative of a constant is 0. So that's
Now, I guess this is strictly for the easy step, but you're supposed to do Alhambra with with the 6x over 6x, and then the derivative of that.
Sure. Yes, you can. Or you can just remember from before. I have polynomial divided by polynomial, which is chapter 2, section I believe 2.5 was the horizontal asymptote. That's the horizontal asymptote. Limit this one over here. So you can just, but yes, you can do one more again. Yes.
When limit goes to infinity becomes constant, what does it mean? Does it mean,
Horizontal asymptote is 1.
does that mean the growth rate is comparable or
Yes. Yes. Comparable. Okay, great. Another question about being with comparable growth rates. Again, we have ln over ln. It's the same function. So polynomial divided by polynomial, comparable. Ln divided by ln, comparable. Polynomial divided by ln, not comparable, all right? They have different growth rates. Polynomials grow faster than ln's. You can have ln raised to 1,000,000 over a linear x. Linear x will eventually win, eventually. You might have to wait a very long time, but when that time comes and linear x wins, it will keep winning from that point on forever, even you have ln to 1,000,000. So growth rates of functions go ln first, then polynomial times ln, then exponentials, and then x to the x. Fair? Now, what's the meaning of this? This question, I believe we did 2.5 is the horizontal asymptotes. This question could be cut and pasted into horizontal asymptote. The reason why it wasn't there is because you didn't have L'Hopital's rule at that time, because you didn't know derivatives, so you couldn't do it. But this now can be sorted as a 2.5. What is the horizontal asymptote for this function? Now, those of you a little bit more vicious about mathematics, go ahead and graph this carefully in your calculator. You will see horizontal asymptote of 1. Whatever function does, it will flat out around 1 to go to infinity, to positive infinity side. I don't know what's happening for the negative infinity because we haven't done. X goes to negative infinity. Might have the same horizontal asymptote, might not have any. But what I need to know is what I do know is that it has horizontal asymptote. Because guys, this over here is a definition for horizontal asymptote. I don't care which chapter, I don't care which calculus, I don't care which course in mathematics. In all of the universe, this is the definition for horizontal asymptote across the board. So as soon as you write this, you are looking for horizontal asymptote. If you end up with a finite number, that is y equal that number is a horizontal asymptote. If you end up with infinity, it's n behavior up, or, sorry, for you, n behavior up, or negative infinity, n behavior down. So you can have those three possibilities. So limit x goes to infinity of whatever the hell is here, it can have three outcomes: negative infinity, finite value, and positive infinity. This would be the n behavior down, horizontal asymptote at that number, and n behavior up. This is 2.5, except now you can do spicier problems, right? Because you know L'Hopital's rule and you can take derivatives and work out more interesting stuff. Bueno?
why when you divide equations, it's not the angle?
What? What angle? These are LNs.
Doesn't one mean the angle is always 1x? What happens if it's 0?
Yes. I know, it's beautiful.
We have very different definitions.
Very different definition for word beautiful?
Right.
Eh. Let's see if anyone in the classroom agrees with me once I write it down.
So this is also going to be one of those ones that we solve. Yeah.
Look at this beauty. So tangent is the graph that goes through pi over 2. Looks like this. They will eventually. I hope. Yes. So this is the cotangent going through pi over 2, for those of you who don't remember it. And we can clearly see that at 0, from the right, we have infinity for cotangent, and then 1 over 0 also infinity. So we have infinity minus infinity case. So what I do is what? Sorry? I can rewrite the cotangent, yes. As what? Yes. I'll kick 3 outside. I don't even know why they bothered putting the 3 there, but that's okay. 1 over x minus cosine x over sine x. Now what? If you remember the situation for infinity minus infinity, we are supposed to factor, which is what makes subtraction into multiplication, and then use 1 over f to create the division, so we have improper. It's a lot of words. In order for us to solve infinity minus infinity, actually, what is the goal? The goal is to go from infinity minus infinity to either 0 over 0 or infinity over infinity. So you have to go from subtraction into division. How do you transform subtraction into division? Well, first you have to factor to make multiplication, and then you will have 0 times infinity, and then you do 1 over f to make it into division. But look at our functions. Now, this question is a little bit not fair for Calc1 class, but this is an awesome question that you guys are asking me for my Calc2. Because there is something that is called Taylor polynomial expansion, which tells us that the linearization of sine x is actually just x, if you do one term. or x minus x cubed over 3 over 6, sorry, for 2 terms and so on. I actually have those notes here. You can see how it looks like. There's a Taylor polynomial. Aha, there it is. So this is a very common trick in physics, done especially for simple harmonic motion or something like that, to linearize nonlinear problems for easier calculation. Replace sine x with x for small angles. And I have both graphs here. The black one is the sine and the red one is x. And you can see that, I put these parentheses. So let's go negative pi over 4, pi over 4, right? On each side, you can see that the red line and the black line are very close to each other, which means that function y equals x approximates function sine x very well for small angles. And here is the full expansion. I was lazy to compute 7 factorial, but you have x minus x cubed over 6 plus x to the 520 and so on and so on. You can go infinitely far. So in order to solve our problem, we can replace sine x with 1 over x because the limit is 0 plus, meaning that you are looking very close to 0, which makes this statement true, and you are actually here right to the next of 0, where these functions are almost identical. So this is the reason why I can say that this is approximately 3 limit x goes to 0 plus of 1 over x minus cosine x over x, which gives me what I need. Now, this is not a fair question for Calc1 unless you ran into this in your physics class. I could argue that you should know this because you did linearization. I believe it was 4.6 when we did the linear approximation, I believe, with the tangent line. Because sine x has the tangent line y equals x at 0. But then it might be too much. Might be too much for Calc1. But Calc2, hell no. This is just a standard good morning in Calc2, And then you go and you brush your teeth and stuff. So I will factor out 1 over x. Is anyone watching stream? One person. If you're a Calc2, I'm going to probably put this on a test. Oh, there was a comment? It says, Dracula, is that you? This is a familiar last name. All right, we'll figure it out. Someone is going to... Oh, that was you.
You were doing Calc 2, and we were doing the project, and we were like, let's do a little comment.
All right. No, it's not me. All right. What I did is I factored out 1 over x now, and 1 over x is going to infinity. Cosine of 0 is 1. 1 minus 1 goes to 0. And we have infinity times 0. So we are going to use the trick now. 1 over f. That's 8. There we go. and I'm going to have 1 minus cosine x remain in the numerator, and then 1 over x is just x right here. At this point, I have 0 over 0. Let me put those red, which is indeterminate form. Which means that I can use L'Hopital's rule. Derivative of 1 is 0. Derivative of negative cosine is positive sine. And derivative of x is 1. So 3 times 0 is equal to 0. So this time around we got that infinity minus infinity is 0.
I'm going. I don't know. When I saw it for the first time, I was like,
No. We don't have to know that.
I'm sorry?
We don't have to know how to do it for the exam.
for exam?
Right.
No, but you want to show off. Oh, by the way, how did the Thanksgiving meal run? Did you pull out any of these things? Still, are you still favorites? So, Jimmy, how are you doing?
You're just making it colder every time you touch it.
No, it doesn't go above 76. Cold.
Such as like you start a fire.
Sure, not
All right. Anything else? Yes.
Let's start with the word policy. Yeah, I know.
What's wrong with you people buying off of stuff?
Did you pull out any fun calculus for your Thanksgiving?
No. Actually, no, I lied. Thanksgiving for me is every single day of the year. I'm serious. I make it out of my day that at least one person, I thank one person at least one day. Once. At least once. And I eat like that every day. So I take off on a Thanksgiving day. I say thank you to nobody. And I eat scrambled eggs on that day. As a protest. Because everyone, you just want to have something different on one day. So since, for me, Thanksgiving is every day, you get the idea. But I did splurge. I put in a mushroom and onion, and it wasn't just scrambled eggs.
You ever do like hash brown eggs?
No. Problem 40 on homework 4.5 says, approximate the change in the magnitude of the electric force between two charges when the distance between them increases from r equals 16 to r equals 17 meters, and the force as a function of distance is given as 0.02 divided by r squared. We have to get into a little bit of physics because this is fun. The force between two objects, in attraction between two objects, could be magnetic, electrical, right? Also gravitational. They all have the same type of the formula with different letters, but they work the same way. So for, say, gravitational force, you have gravitational constant g, mass 1, mass 2 divided by the separation squared. So as soon as that formula shows there, you'll see you have two masses, m1, m2, and those would be the masses of the objects, so let's say Earth and a sun, and you can figure out the gravitational force, right? The attraction between the two. You have the same one for the force for electrical, right? Which is as the electrical constant now, and you will have the charge 1 and the charge 2 divided by the separation squared. There are many of the formulas, they all look the same, just different letters, and it's attraction between the two objects. So now, as you can see, all of this is already calculated for you into a single number, 0.02, and all you need to work now is the r squared. Clearly, as the distance increases, the force between two objects should decrease. I believe there is a similar formula for romantic relationships as well, as the love between two partners decreases as the separation between them increases. And it also goes as a square. So as soon as one moves further away, it just, it just dies. So it works across the spectrum. So now what we do here, we know that our formula for, you are going to use the differential to approximate, because they want approximation, they don't want the exact. You can calculate the exact one easily, right, by just figuring out delta f. If you take the f computed at 17 and then subtract f computed at 16, right, in which case you will have to square 17 and square 16 and divide into 0.02 and so on. So yeah, calculator work, but you can get exact. That's the exact one. We don't want that. We want to approximate. And we do that by figuring out dy, well, in this case, df, which is given as the derivative of f computed at 16 times the change in r. Now, change in r is very simple. 17 minus 16 is 1. Actually, sorry, 16 minus 17. Oops. Negative 1. And we also need the derivative of f in respect to r, which is going to be 0.02 is a constant, and then times negative 2 r to the negative 3, which is r cubed. Oh yeah, I had it right. I don't know why it's changed. 17 minus 16 is 1. You're right. So here's our derivative. So df is equal to negative 0.04 divided by r cubed, which is 16 cubed, times 1. This is negative 0.04 divided by 16 times 16 squared. I want to cancel these guys. Negative 0.01 divided by 4 times 2, 56, which is 1024. So it's a small number. You can compute that. This is roughly what? It's something. Whatever it is. So that's one. The hell touchscreen? Like you pay like $5,000 for this nonsense. You don't even have a touchscreen thing. Oh. So, this is problem 7 on the homework. It says function s of x is given as 3600 divided by 60 plus x, gives a person's average speed in miles per hour if he or she travels 1 mile in x seconds more or less than 60 seconds. Use a linear approximation to s at 0 to find the person's approximate average speed if he or she travels 1 mile in 55 seconds. What is his or her exact speed?
Isn't that really strange the way it's worded? So I read it too, and I was like, what?
So let's read it again. So the function s of x gives the person's average speed in miles per hour. Miles per hour. If he or she travels 1 mile in x seconds more or less than 60 seconds.
Can we skip it? Can we not do this one?
You can skip it, yeah, it's fine. You can just zone out. Use a linear approximation to s at 0. All right, we'll just use a linear approximation to x is 0. That's just going to be a quick tangent line problem. We're done, right? Let's do it. I'm going to rewrite this function so it's easy to take the derivative. I don't want to do quotient rule or anything like that. Just a constant. So s prime of x is equal to negative 3600 times the derivative of the inside. Wait, hold on, that's it. Times the derivative of the inside is 1. So we have negative 3600 divided by 60 plus x squared. So what is our linearization in terms of x? It's going to be s computed at 0 plus s prime computed at 0 x minus 0. That's the linearization. Okay, so let's see. S computed at 0 is 60. Well, let me write it. 3. I'll write all the steps. And now we have the derivative computed at 0. Oh, I was supposed to put 0 there. So I have 3600 divided by 60 is 60 minus 60 squared minus x. Good? Everyone happy? So this is our linearization. Use a linear approximation to S at 0 to find the person's approximate average speed if he or she travels 1 mile in 55 seconds. So, what now? I'm sorry? Plug in 5. 55. Five miles per hour. Which it should put you at ease, right? Because that is actually what we do. If you walk a mile, it should take you about 20 minutes. There are 20, so you can do 5 miles per hour to walk. Sounds good. Bulletproof. For the function f given below, find the antiderivative which satisfies f of 1 is 1. F of x, x to the 5, minus 2x to the negative 3, minus 3. All right. The antiderivative. Integral of f of x dx is equal to the antiderivative f of x plus c. These functions, lowercase f of x and capital F of x, are related. They're not the same. They are related by the fact that the derivative of f of x is little f of x. And we will talk about this much more next class in 5.3, Fundamental Theorem of Calculus. We are going to have this down 100%. Right now, what we want to know is the antiderivatives or integrals would undo derivatives. So, what I need to do is I need to integrate x to the 5 minus 2x negative 3 minus 3 dx, and then I need to find that value c by using the condition that it's given to us as capital F of 1 is 1. So now I will integrate using the formula we learned last class, that the integral of x to any exponent is x to the n plus 1 divided by n plus 1, and then we put plus c at the end. So in the first problem, x to the fifth, this n is 5, so I will have x to the 6 over 6, because n is 5, 5 plus 1 is 6. Minus 2, copy the constant, and then now we have n to be negative 3. Negative 3 plus 1 is negative 2, so I have x to the negative 2 divided by negative 2. And finally, minus 3x, and we put plus c. So derivative of constant is that constant times x. So negative 3x. If you're still a little bit confused about that, I will show one more time what I did last time with the 0 and 1 and so on. So now, these guys cancel. So I'm getting that my antiderivative function f is x to the 6 over 6 plus 1 over x squared minus 3x plus c. And we can use the fact that f of 1 is 1 to compute the value of c. So this is replaced by 1, and every x we plug in 1, so 1 over 6 plus 1 over 1 minus 3 plus c. So guys, this is your x, and this is the f. It's just a notation for a point. It's just bad it's 1, 1, so I can't really show. But it's 1, 1. It's a point in xy plane. So now, 2 and 5/6, right? 17/6. You subtract 1 on both sides, right? Then you add 3 to both sides. So 3 is equal to 1 over 6 plus c. c is equal to 3 minus 1 over 6, which is 2. And 5 over 6, 12. And 5 is 17 over 6. So what is the antiderivative? The particular solution, it's x to the 6 over 6 plus 1 over x squared minus 3x plus 17 over 6. So to put this a little bit into perspective, especially you're trying to figure out how come the point x comma y plays a role in all of this business. And since this is a review class, let's just talk briefly about that. So I have y equals x squared, which is a parabola going through 0. And then I have y equal x squared plus c, which is actually infinitely many parabolas. This plus c is actually a shift up and down of the same x squared function. So if I am to draw a coordinate system like this, x and y, and give you an arbitrary point xy, like we had 1, 1, but you can have anything, you have to understand that only one out of all of these functions, infinitely many of them, only one will go through that point. So that's why you are able to find the particular solution out of infinitely many solutions, because you had this one point. You know how the graph looks like, and all you need to do is to shift it up, shift it down, so it fits through that one point. Let's say it looks like this. Let's say. So we have the notion of a basic function x squared from Precalculus course. And now when you integrate 2x, you will get x squared plus c. Now that plus c is a shift up and down, and since c is not given to you, you have to assume all of the infinities of x squared, they all have vertex on y-axis. But there are infinitely many of them. As soon as this extra point is given to you, you are able to compute that c. And that c is simply shift up or shift down, depending on where the point is. This will be extremely, extremely important for your differential equations course, those of you going there. Right now, obviously you have a problem on a test about this, and then if you go to Calc2, obviously you'll use it again. Happy? Good. Yes?
How do you translate the logarithmic differentiation into a simple function?
4.3 is graphing functions.
Yeah, but,
And you want to take all of the derivatives using the logarithms, right?
yeah, but I'm wondering, like, kept change into a more simple form, but I had no idea the logic behind it. I want to know how to get this through. Yeah, I don't understand the process one because when you're supposed to be on the logarithm,
Just write it down. All right, so we're going to do some. This falls under the category of housekeeping. So as you take derivatives to find, the critical points and inflection points and to do all of the first and second derivative tests, you might opt to use logarithmic differentiations because you don't have to mess with chain rules and product rules and quotient rules, nothing. You just, as like you say, just do it. But then you end up with something like this. Now this is cool for figuring out your critical points because it's already in a factored form. You set this one equal to 0, you set this one equal to 0 separately, and you get your critical points solving equations. So this is, doing the logarithmic differentiation is superior over anything else because you already get the answer in a factored form, which means that it is the fastest possible way to get that. The problem with this is, right, there's never a free lunch, is that when you have to go to the second derivative, right, not fun. I'm serious, not fun, right? Look at it. So, now you guys are making me laugh. I have to be serious. It's serious business. It's second derivative. It's acceleration, all right? You want to sit over there? No. Okay, then. And I have to stop bothering you because you have to focus. Hey, you have a set of words you'll make? Good. The rest of you spoke already. What was something else? Oh, yes.
Second derivative.
So now, if I need to get the second derivative, well, I'll have to multiply this out and get it into a better form because really, second derivative means the product rule with a whole lot of mess now. So what I'm going to do is FOIL. (2x squared over x x minus 2 minus x squared, x minus 2 squared. And now I need to put this in a single fraction. So least common denominator is x minus 2 squared. The first one is missing x minus 2, and the second one is missing x to get to common denominator. So now the common denominator is x minus 2 squared. When I FOIL the top, I get 2x squared minus 2x cubed minus 4x squared minus x cubed, which further gives me 1x cubed minus 4x squared. I can factor out x. I can factor out x squared, but I don't need to. I just factor out 1x because that's how much I can cancel. These cancel. And now I have my first derivative written as x squared minus 4x divided by x minus 2 squared. And now it's, I mean, you can still factor a little bit more, it's okay. And now it's again in a simple form to take the second derivative by log. It's just going to be this times 1 over x, another 1 over x, 1 over x minus 4, and then 2 over x minus 2. So that's the reason why I did that.
Do you want to do the same with the second derivative so that when we're trying to figure out the inflection point?
No. The reason why I'm doing logarithmic differentiation is as soon as I'm done with logarithmic differentiation, it gives me the problem in a factor form. Each factor gets set equal to 0. That's why I don't want to do this one. I could have gotten this result, but then I have to set this equal to 0, right? Taking the derivative of this might make it worse. You know what I mean? So for exam coming up next week, we are going to look at the first derivative test, second derivative test, min-max, graphing functions. That's 4 problems that are all related to graphing functions. And I said that all of those problems will be separate. So you are not going to have a 45-minute problem where you have to find everything and graph the function at the end. Because if you mess up on the first part, finding, let's say, first derivative, the entire problem is just done, which you might realize when you're ready to graph, and then you simply don't have another 40 minutes to redo it or fix it. So what I do for exam is I break that one 40-minute problem or 45-minute problem into 4 separate problems. One problem will say, do the first derivative test, which means you have to go and find the first derivative. You have to go and find critical points. You have to go and make the graph and find all of the parts where the function increases and decreases, and also state which one of those points is a min or a max because you are looking at the graph. So the first derivative test is not just take the first derivative and say, yep, I got the first derivative, right? It is first derivative, then critical points, then the graph not the graph of the function, but the diagram, right? With where you plug in your critical numbers and you plug in the vertical asymptotes, and then you test for increase, decrease. I hope you know which one I'm talking about, the ones that look like this eventually. Right? So there will be a problem that has the first derivative test. Then you have the second derivative test, separate problem. Different function, okay? Nothing to do with the other problem you already did. You are taking the first and then the second derivative, and then you are doing this for concavity. So you'll find inflection points. You will partition using inflection points and vertical asymptotes. You will test concave up, concave down, and you will, as the answer, state the intervals. So you will say function is concave down from negative infinity to 2, concave up from 2 to 7, and then concave down from 7 to infinity, right? Something like that. So the entire problem consists always of figuring out the derivative, figuring out points, working out the graph with tests, and then stating the answer, which are the intervals. You will say function is decreasing from negative infinity to 0, and then increasing from 0 to 5, right? So you have to write that. That's the answer. I think that's exactly how I see. Right there. Conclusion. And I wrote it in red because this is the answer. All of this is partial credit. This is the answer to the question where you say that the function is decreasing on the interval x1, x2 from negative infinity on x to 0. The function is decreasing, and then the function is increasing on 0 to infinity. From 0, x to 0, to x infinity, function increases. So that's how answers look like. The second derivative test does the same thing. I did not make it red, but you still have first derivative, second derivative, find the interval, right? We found only one inflection point at 5. We picked 2 test values, plug those test values, concave down, concave up. And now, the conclusion is right here. Concave down on negative infinity to 5, which is the x interval, and then again x and x, x1, x2. So from 5 to infinity on x-axis, from 5 to infinity is concave up. Separate problem to find min and max, which is you take the first derivative, and then find the critical points. Critical points can be min, max, or inflections, so be careful. And then you have to figure out whether it's a min or a max. You can use the first or second derivative test to figure that out, whatever. And then the fourth problem is for you to graph a function. I will give you all of the information, which means I pick a function and I actually solve the entire problem. I find everything. X-intercepts, Y-intercepts, asymptotes, concave up, concave down, increase, decrease. I do 100% of the work. Well, I do 95% of the work, and I ask you for those 5%, okay, for full credit. I will give you in a chart all of the information that I find for that problem, and I tell you, here's the information, draw the graph. So that's just for me to see that you guys are able to draw the graph when you find. What?
We draw a graph.
Draw it.
Like a line graph or like an actual like body graph? Like,
Yeah, the one that goes, whee! Yes. That's the one.
not the line graph.
No. You see this list? I do this for you. And then you use that information to draw that. So I do this work, I do this, I do this, I do this, I do this, I still do this, I still do this, I still do this, that, and then you draw that from what I did up there. That's a fair trade. So I will tell you vertical asymptote is at -2 and +5, horizontal asymptote is at 1, x-intercept at 3, y-intercept at -7. increase, decrease intervals, concatenate intervals, and you just, as the artist, pick up your favorite color. So that's how the problem is going to be divided over 4 problems. And then there's going to be a problem on optimization, word problems. So we talked about farmers and money and oil and all that cool stuff. Word problem, like we just had on charges, right, for the differentials. Linearization, which is technically a freebie because you guys are getting the intertangent line. You had that on your previous test. And then integrals with the plus c. And L'Hopital. It is potentially a very long test. 3 hours. 10 problems. Again, depending on spiciness, you might have the replacement problem. Standard stuff. What? So, any other questions about the exam? It's going to be in this room, yes. Yes. Whatever you want to do, I will definitely do one after the test. But the one who's on the test, definitely will be the other. Well, actually, I can log in. You had my problem. My MATLAB? Yes. It's not fine, though. Good. That on it?
No. So like tomorrow
And maybe I can give it to him. Optimization. See how it's front of me. That's okay. All right, here, study plan. And then the stuff just popped by. How do you use this? It's supposed to be user friendly. Okay, so I would say this for the record. One of the top 10 reasons why I hate Mac is because I can't figure out how to use the damn thing. All right? Probably. I tried to just click on the study plan and just thing popped up.
it's my desktop.
Oh, your desktop is a rectangular pen built. Okay, here it is. The farmer problem. We opened up random one, 14. So here is one of the optimization problems. Maybe we do two, huh? Oh. A rectangular pen is built with one side against the barn. Does not require fence. If 700 meters of fencing are used for the other three sides of the pen, what dimensions maximize the area of the pen? So here we have the barn, and we are fencing off area like this, x and a y. So x plus 2y is 700, because we have 700 meters of fence. Now, we want to maximize the area whose formula is xy. We know that we are supposed to solve for one variable and plug in. So 700 minus 2y times y is equal to a max, and then we differentiate. You differentiate in terms of whatever variable you have, in this case y. So we have d dy of 700y minus 2y squared equal to a max derivative of 700y is 700 minus 4y equals to a 0. That area is some number. I don't know what number, but whatever number it is, the derivative of it is 0. 4y equals 700. Y equals how much? Half is 350. Half of 350 is, very good, meters. So we have that y is equal to 175 meters. And then we can compute x by simply using 700 minus 2y, which is 350. And we will say that dimensions of the largest, right, would be, so if this is, again, the barn on top, so this is 350 meters, and this is 175 meters. The part B of this question is asking what is going to happen if they so you still have a barn, but this time he wants to create 4 bins where each one will have area of 225 meters squared. What dimensions of each pen that minimize the amount of fence? So now I will call x and y, and we'll have x, 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 and then y, 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 right? So if you look at this, I want 4x's plus 5y's to be minimum, and I have that x times y is 225. Now, why in the world would something like this be even remotely plausible for someone to compute? Well, we all know that if you are, let's say, planting, well, we should know, if you are planting tomato or strawberries, I don't care what it is, you have to have a certain separation between those plants because you don't want them to compete for resources, for water and food and nutrients and stuff like that, right? So if you are planting stuff, right, you put one there and then the next one and the next one, right? So you can actually rearrange them in a, so you can figure out what is the actual area that you need just by figuring that out. So this is why it might be so specific, 225 and whatever. Now, you want also to minimize the amount of fence used to go around it so the rabbits and deer don't make mess there. So you have these two. Again, process is the same. Solve for x or y, doesn't matter. And then plug in. So 4 times 225 over y plus 5y is minimum. So that's 800, 900 over y plus 5y is a minimum. And then we differentiate in terms of y. Negative 900 over y squared plus 5 is equal to 0 when you take the derivative. I'm just going to say that 900 over y is the same as 900 over y to the minus 1, whose derivative is 900 negative 1 times y to the minus 2, just in case that you are not following the derivative from chapter 3. So now we have that 900 over y squared is equal to 5. I move negative 900 to the other side, becomes positive. So 5y squared is 900. Y squared is 900 divided by 5, which is 180. Then we square root both sides and we draw plus and minus, keep just the positives because y is positive value. So square root of 180. Square root of 180, so 9 times 20. So 3 times 2. Root 5 is 223. No. About 13 feet. So y is about 13 feet. Oh no, meters, sorry, meters. 13 meters. And we can take our 6 root 5, which is the exact value, and plug it back in our x225 over y. What happened? Yeah, 6 times 2.23, square root of square root of 5 is roughly 2.23, so about 13. I don't think you would measure all the, quarters of an inch as you are putting up the fence. So it's good enough. 2 plus 2 is 4 plus 5 is 9. That's divided by 3. So 73. divided by 2 root 5, hit it by root 5. It's 73 root 5 divided by 10, which is 7.3 times 2.3, 14, 15, about 16. So roughly 13 by 16 each one. Those will be dimensions. Roughly. We can find the actual value by punching values in a calculator. I have 16.32. 16 is good enough.
How do you decide like which one is minimum, which one is max? You find the derivative is zero.
Well, we only got one value. So if you only have one value as you compute your derivative, you get one critical point, and the problem was calling for min or a max, right? We're done, right? The issue is if you get two, where one is a min, one is a max, then you have to do first derivative test or a second derivative test to show which one is min, which one is max, because obviously one point you will have to. Say you want to maximize your profit as you are selling a product, and you get two critical points for two different x's produced, number of units produced. One gives you min, one gives you a max. You don't want to mess with that. You actually need to know which x gives you a min, which x gives you a max. In this case, problem called for the minimum amount of fence. And the only value we got was y equals, where is it? 6 root 5. Clearly it leads to minimum because it was the only value there. In a previous problem, it was calling for maximum area. The only value we got was y equal 175. Clearly a critical point leading to a max area. But if you got y1 equals 175 and y2 equals 230, let's say, that 230 could be a lower minimum or it could be a maximum. And you can't put both of those answers, right? Because one is going to be better than the other. In that case, you have to do first derivative test to determine min and max. And then once you have them, if they're both min, you will have to compute the other value and see which one of those gives you the better option. Right? Yes?
You just compute them either way, right?
Yes.
Yeah.
You just compute the other coordinate. So you multiply x times y, which one will give you bigger area. So they both could be maxes. Maxima. Maxes in the system. That's the optimization problem. Well, two of them, right? Anything else? Yes.
I don't remember the number, but I have like kind of written down. It's that thing where it's like the woman's on the boat, like 3 miles from the shore, and the shore is 9 miles from the dock, something like that. She rows 2 miles an hour. It's the thing where you have to write out the triangle and figure out what's the most time efficient. Yeah.
I did that at the oil rig, and
Yeah, that's what it was. Still, what?
Cool.
anything else?
Knowing your last theory exam.
Yeah,
For
that'd be awesome.
example,
What happened?
Can we have a sample for the exam?
I don't know.
Oh,
My
prepare.
MATLAB has the sample exams. If you really want to practice, you can take those either pre-tests or post-tests, and it will grade you and it will tell you. That's only reserved for those who don't care, right? So I have the quizzes that will start tomorrow, which in a sense prepare you, obviously, because you'll learn, hopefully, from those. Are there any more problems before I demonstrate stuff on my MATLAB because of the stream? Are we good? So we did do differential. We did linear approximation with the person that was running or walking, whatever. We did optimization problems. I did talk about first, second derivative test and derivatives. We did do a few derivatives. We did the integration. I think we, and L'Hopital rules, like 5 in the beginning of the class. I think we covered everything, yes. Oh, intermediate value theorem questions. If I need to, I can put them in. Intermediate value theorem was the relationship between, so intermediate value theorem was the relationship between instantaneous and average rate of change. Instantaneous rate of change is the derivative, and average rate of change was that difference quotient. So MVT, mean value theorem, stated that if the function is continuous and differentiable, we have that f of b minus f of a divided by b minus a, which is the average rate of change, that's your difference quotient, is equal to the derivative at some value c, where this c is in between a and b somewhere. So that's the mean value theorem. So, I don't know. Find C for f of x equals to x cubed minus 2x plus 1 on, I don't know, 1 to 5. No, it doesn't matter. So what we do is we find f of 5 minus f of 1 divided by 5 minus 1 equal to the derivative of f at that mysterious value c. So f of 5 is when you plug in 5, so 125 minus 10 plus 1 minus everything computed at 1, which is 1 minus 2 plus 1, divided by 4, needs to be equal to the derivative, which is 3x squared minus 2, but we have to write it as 3c squared minus 2 because we are plugging c into the derivative. So now we just compute. It's 116. These all cancel. Yeah. 116 over 4 is equal to 3c squared minus 2. Oh, 116 is divisible. That's 25 and 4, 29. So 31. C squared is equal to square root of 31 over 3. And we should put plus and minus We should put plus and minus. But I'm not going to put plus and minus because our interval was 1 to 5. And that's clearly positive value, so whatever the negative of this is, no one cares. 31 divided by 3 is like 30 divided by 3. 30 divided by 3 is 10, and square root of 10 is 3.2, whatever. So there you go, about 3.2. So C is the value at which the instantaneous rate of change, which is the derivative, and the average rate of change have the same value. So that's the intermediate value theorem. And I noticed throughout the year is the only issue you guys might have with it, well, apart from memorizing the formula and the definition where the conditions have to be that the function is continuous and differentiable. I might just be that mean and evil and put 1 over x from minus 1 to 7. Mean value theorem doesn't apply because the function is not continuous at 0. You see that? And you can solve that problem just by writing a sentence for full credit, not continuous at 0, therefore MVT does not apply. I said, if I want to be mean and evil, that would be it. Because some of you would spend like 30 minutes computing a value, get 7, but it makes no sense because it's discontinuous. You have to learn theorems and definitions are important because if you don't learn the conditions under which they apply, then it just doesn't look too smart, right? How many of you walk with the umbrella? You know, when it's going to be nice, sunny weather, right? Have to have conditions to walk around with an umbrella. Right? Right?
What if, like, we're vampires?
Don't go out, man. All right. See, this is why I do mathematics. Because there's no discussion and your opinion doesn't matter at all. No one's opinion matters. 1 plus 1 is 2, and no one cares what you believe in or what your feelings are. Right? It's just 1 plus 1 is 2. And here are the conditions for mean value theorem. Function has to be continuous and differentiable on A to B, done deal. Right? Discussion closed. Any other questions before we jump into my MATLAB real quick? No questions? All right. Bye-bye, stream.